The aim of the committee is to promote and facilitate scholarly cross-departmental interaction among members of the MIT community. To this end, we are delighted to have with us today Professor Susan Solomon. Professor Susan Solomon is the Alan Swallow Richards Professor of Atmospheric Chemistry and Climate Science at MIT. Before coming to MIT, she spent most of her career at the National Oceanic and Atmospheric Administration, a federal agency focused on the condition of the oceans and atmosphere. Professor Solomon is most well known for her work on showing the correlation between the use of CFC or chlorofluorocarbon and ozone depletion. Professor Solomon is a distinguished scientist and a member of several leading scientific organizations, including the United Nations National Academy of Science. In 2008, she was selected by the Time magazine as one of the most influential people in the world. Without further ado, please join me in welcoming Professor Susan Solomon.
Thank you very much. It's certainly a pleasure and an honor to have a chance to talk to you tonight. The organizers asked me to say a little bit about my life in science, and to do that, I'll spend quite a bit of time on stratospheric ozone depletion. I also really wanted to give you a sense of why, for me, studying the science of our planet has actually been a very uplifting experience, and why I think that our interest in environmental challenges, which used to be actually quite strong, say 30 or 40 years ago, we had a much more optimistic view, I think it's fair to say, about our ability to solve problems as they arose. I think that we are learning to be interested in such problems again. I'm going to talk a little bit about the way that that sort of progress was made and the sort of things that I think will be required, the ways in which I think MIT can contribute to that, because I also have the honor of leading the MIT Environmental Solutions Initiative, which was just announced last April, and I'll say a little bit about that. I'm not going to talk for very long about climate change. I'm just going to mention a few points about that. I'm going to spend most of the time on the remarkable story of lead. Many of you may know that it used to be in everything from paint to gasoline. In fact, it was marketed as ethyl. Tetraethyl lead was the constituent in gasoline that was an anti-knock agent, and turned out to be an enormous environmental problem that we actually did solve. And I'll talk a little bit about that too. So, lead. What really was it? It was an amazing success story in understanding risks, even when at first they were really hard to ponder. That sound like anything familiar to you? Maybe climate change? The effects of very heavy exposures to lead were well known. People who, for example, worked in smelters or made batteries or leaded crystal or were welders, those sorts of people were well known to suffer from lead poisoning. But the environmental effects through things like lead additives in, at that time, white paint, including indoor paints that would chip, and kids would eat paint chips and get very sick, were not known. Gasoline additives, as I mentioned, lead pipes, and even, if you go far enough back, lead dishes were actually used by the Romans. The fact that those things could also be damaging, that there was not just an occupational hazard, but really a widespread environmental hazard, was not understood. So what does lead poisoning do to you? Well, it can indeed kill you. It's in large enough quantities. It can also cause all kinds of problems of your digestive system. It can damage the nervous system. It can damage your kidneys, and it can actually also reduce your IQ. So knowing that I'm talking to a bunch of relatively younger people, if you guys think that your parents are dumb, it might indeed be because they were exposed to a lot of lead when they were young. Because you don't have that problem anymore. Lead is not in gasoline anymore. Where did the earliest interest in lead as an environmental issue begin? It's probably the studies by Pliny the Elder, who noticed that using it in cooking utensils kind of seemed to be making some people sick. Of course, back in those days, people didn't live that long, so the time scale on which they were dying of other natural causes was fast compared to the time scales in which we're exposed to it in later years. Lead acetate, remarkably, was actually added to some wines as a sweetener because it is actually sweet. That's why kids ate paint chips that had lead in them. Compounds can be quite sweet. An interesting case is that in Devonshire, in the UK, people were using lead weights to crush apples to make apple cider. And so one scientist thought that maybe that was what was making so many people in Devonshire sick. And interestingly enough, there was a rebuttal to Baker's ideas about this. So this is sort of the first lead skeptic rebuttal, which I just thought was kind of fun to put out there. So what were the criticisms of the idea that lead could be damaging to people in those sorts of forms? Well, you know, it's natural. There's lead in the environment. It's not something that you make in the lab. It's something that you dig up. Some scientists believe that the body could adapt by expelling excess lead. So if you were exposed to just a little bit of it, your body would basically get rid of it. Another issue that was raised is, well, how much is too much? If you can't define a threshold for danger, why should you worry? Sounds kind of familiar too, doesn't it? But it became clear that this argument that it was natural and that the body could adapt was a little flawed. People began to do things like look at the blood, teeth, and hair of modern children. So people would collect, for example, teeth of kids and compare that to the teeth of, say, Chilean mummies that were from thousands of years ago in a very pristine environment. And what they found is that the body wasn't getting rid of all the excess. It was actually accumulating in the children. Advances in geochemistry, particularly the use of clean room technology, was extremely important in this issue. I teach a lot about this in my class, Science, Politics, and Environmental Policy, where I really go through this in detail. But just to give you the basic point here, back in the day when people were using lead in gasoline, there was so much lead everywhere in the air that the ability to actually make a measurement of how much lead might be in a sample, in a piece of food, or in an ice core, was severely compromised just by the background level. So it wasn't until geochemists began using clean room technologies to get at this problem, and the reason they did it was because they wanted to measure lead at very, very high accuracy and precision because they wanted to get information about the age of the Earth. So they were asking a question that required a level of cleanliness that was just way better than what people were doing at the time. And sure enough, those people then noticed that there was a real problem in the measurements that had been made on lead. What they did then was to do things like dig up ice cores. This is from an ice core in New England, and show that as human beings began to mine metals, the amount of lead increased and increased until about the time that it went into gasoline, and that's what happened. So you can see the tremendous increase associated with human use of lead. But you wouldn't be able to see this unless you did it in a clean room. Well, another very important issue, and it really shows how connected our science can often be to social issues and to issues of equity, is the fact that there was a civil rights connection in this problem. In particular, in the 60s, people began to become very interested in civil rights, and they also noticed that blood lead levels were much higher in children living in old homes, in poor areas. And so, not surprisingly, poor black children in urban areas, particularly near highways, had the highest lead levels of any kids. So the level, for example, of kids with more than 25 micrograms per deciliter in their blood for poor kids in urban areas is almost 10 times higher than for the general population. So as that realization dawned, and maybe I'll just show you this, lead began to be phased out of gasoline. And at the same time, through, I think, the precedence of the Surgeon Generals at the time, blood lead levels were being measured in kids' bloods in school. And I actually remember doing this even myself. So what happened is that the amount of lead in the gasoline went down, and there was a very, very strong relationship to the amount of lead in kids' blood. Well, that was a tremendous understanding then in science, is allowed because of advances in epidemiology, is possible because of advances in epidemiology, advances in geochemistry, as I talked about, development of alternatives for paint and gasoline. Nothing happens in an environmental problem until people perceive the solution as practical. I often tell my class that. They also have to perceive the issue as being personal. And so, for example, the fact that the lead levels in their kids were related to how much was in gasoline was very personal. And the issue has to be perceptible. It didn't become perceptible until geochemistry was able to show that it was. And epidemiology is what allowed studies of things like the children's IQ to be related to the amount of lead in their blood. It's really an interdisciplinary success story. We wouldn't have been able to have this advance if we didn't have all of those disciplines working together. And this is a little hard to see, but what it's showing you is the phase out of lead in gasoline as a function of time in various countries. So pretty much now, just about every country in the world has phased out lead. We were fairly early in that, in gasoline. There are a few countries that still have lead in gasoline, even to this day, which is really quite amazing. And they basically are places that don't have the institutions in their governments to actually deal with environmental problems very well at all. So it's places like North Korea, Myanmar, I believe Algeria, which actually is one of the ones that surprises me. I don't quite understand why that's so. So there are some really clear connections to institutional capabilities. So that's a great example of a triumph, I would say, of environmental science and policy, different sciences working together to really help solve a problem that was very acute. Now I'm going to talk about another area where we've managed to have some tremendous success, and it is in our changes in what we do that have to do with the stability of the Earth's ozone layer. Ozone, as you probably know, is very important to the health of the planet. It's basically thought of as being Earth's natural sunscreen, so it's absorbing certain wavelengths of ultraviolet light that no other compound absorbs. If you didn't have an ozone layer, basically the biological life as we know it would not evolve because it wouldn't thrive. So as the ozone layer gets depleted, the amount of UV exposure goes up, and that is clearly not a good thing. I don't want you to get too confused by the sorts of different environmental issues around ozone that you may hear about. Having ozone in the ozone layer up in the stratosphere, which is about 10 to 25 kilometers above our heads, is a good thing for our planet's sunscreen, as I mentioned. Having high ozone levels in the lower atmosphere, the troposphere, is not a good thing because it's a greenhouse gas, and it can get even very, very ugly in smog situations like places like Los Angeles. So just as a mnemonic, that's how you should think about ozone. Tonight we're just going to be talking about the good ozone in the stratosphere and the measures that have been taken to protect it. So I've already mentioned that the ozone layer's key role is to protect us from UV. What it doesn't do is to actually contribute significantly to the greenhouse effect. So it's not really a big player in the global warming issue. We have plenty of evidence. It's a very personal thing that we all, I think, have experienced and know about that UV is bad for you. And we're not surprised when we learn that too much UV will cause skin cancer and eye damage. So there's no difficulty understanding this environmental issue as a very personal one. The interest in the stability of the ozone layer really dates back to 1974 when Molina and Rowland published this paper. And what they said was that the chlorofluorocarbons, which were being used in many applications at that time, mainly actually in spray cans, so things like underarm deodorant, hairspray, paint, oven cleaner, everything that came out of a can, the propellant in the can was chlorofluorocarbons. They were also used in refrigeration, air conditioning, foam blowing, but mainly at that time it was spray cans. They pointed out that those molecules had very, very long lifetimes in our atmosphere. They could live as much as 50 to 150 years. And that meant that the chlorine in those molecules would have no other place to go but to rise up into the stratosphere. The chlorofluorocarbon would break down the high energy ultraviolet light if it got high enough up. Chlorine atoms would be made. Chlorine atoms react with ozone to make chlorine monoxide. Chlorine dioxide and reacted O to make chlorine atom back again. So the net of those two reactions is a catalytic destruction of ozone. It's catalytic because this chlorine atom can go back and go around and around this cycle many, many hundreds of thousands of times. And this paper also has a little lesson for graduate students, which is that you should always read your papers very, very carefully, because you never know when you're going to win the Nobel Prize 20 years after you publish a paper, and you really wouldn't want to have a typographical error in the paper. But it doesn't actually stop you, as these people have provide evidence for it. You'll get your Nobel Prize anyway, just lets people make fun of you. So these are reactions among gas molecules only. This is pure gas-based photochemistry that I'm talking about. They published this in 1974, and prior to 1985, we expected about a 3 to 5% depletion of ozone by about 2100 if we kept using chlorofluorocarbons at the then current rates. So it was only a theory, it's far in the future. Some other issues people talk about. But then something really amazing happened in a very unexpected place. So I want you to remember these dates. Paper published in 1974, 1985, up to 1985, we thought a few percent in 100 years. And then the Antarctic ozone hole was discovered. This was in the end of 1985. I was a young scientist at the time. I was 29 years old, new math. And it was an incredible experience to be a young scientist with a newly minted PhD in atmospheric chemistry when this incredible game changer came along. The beautiful satellite images from NASA are sort of the iconic way that most people know about ozone depletion, but it was really a ground-based system that was responsible for our discovery of the ozone hole. These are measurements made by the British Antarctic Survey. They have a little station right there, and they started monitoring total ozone in the late 1950s. For the first 20 years or so, a little bit more, a little bit less from one year to another, but not much trend. And you don't have to be a statistician to know that this is a remarkable change that happened basically in the 80s and 90s. And I'll show you some more data from the Japanese station and the American station. So it was very clear that something amazing was happening to the Antarctic ozone. And what was it? Well, I got very lucky at this point. I came up with an idea about a mechanism that might explain it. And my insight really was the fact that while Molina and no1 had talked only about gas-phase reactions, you could think about the fact that polar stratospheric clouds exist in Antarctica. It's so cold that clouds can actually form in the stratosphere. The stratosphere is extremely dry. So if you go into the stratosphere over Boston, you will not find any clouds. You find them in the troposphere where it's much wetter. You won't find it in the stratosphere. You find them occasionally in the Arctic, and you find them in spades in Antarctica because it really truly is the coldest place on Earth. And those clouds allow a surface reaction to take place, which is this one. I'll show it in the framework for people who are seated over here can see more easily in a minute. That's basically hydrochloric acid can react with chlorine nitrate to make molecular chlorine. And that is the start of a process that allows surface chemistry, heterogeneous chemistry, where gas molecules go to the surface of the particles, react, and turn into something else that then goes on to deplete ozone much more effectively than would happen if you only had gas-phase reactions. So the clouds are sort of like the potion in the Jekyll and Hyde story. They take something that wasn't so much of an issue yet turn it into something which is very much more of a big deal. So how does this work? The chlorofluorocarbons go up to the stratosphere, chlorine gets released, a substantial amount of that chlorine turns into hydrochloric acid and chlorine nitrate. To the extent that that happens, the ozone layer is safe, because those are stable molecules. You've all worked with HCl in the laboratory when you were studying chemistry. So they're reservoirs for chlorine, but they can react together on the surface. They don't react together in the gas phase at all. That makes molecular chlorine, which is a gas. And it's a gas that can break down with sunlight very readily. So it photolyzes and makes chlorine atoms. The chlorine atoms react with ozone. I already showed you that reaction. That makes chlorine monoxide, and there are other processes that happen that I'm not going to go into. But this is the beginning of the catalytic cycle that's going to end up destroying ozone very, very effectively. At that point, the chlorine's been activated for ozone loss, so it's been changed from being an inert reservoir into something that's activated and it has the capability to destroy ozone. So the ozone layer, we don't talk about it as a layer for nothing. If you look at the amount of ozone in the atmosphere as a function of altitude, most of it is in a layer between about 15 and 25 kilometers. There's the ozone layer. The gas phase chemistry can only destroy ozone up here for reasons that I don't have time to talk about in detail, but that's the no1 and no1 chemistry. And if that were to happen, you only get to nibble away at the neck of the ozone layer, destroying 3 to 5% in 100 years, as I mentioned. But when the polar stratosphere cloud surfaces activate the chlorine much lower down, right in the heart of the layer, they actually take out essentially the entire layer. So you get to a point where almost no ozone is present at the height range where the clouds occur, and this is the coldest part of the Antarctic stratosphere. So I also had a wonderful experience, probably the most amazing experience of my scientific life, was going to Antarctica and being able to make some of the first measurements that actually showed that this chemistry is what's going on. I went not to the South Pole, but actually over here at Monroe Station. So the way you go to do that is they fly you down to New Zealand via standard commercial airline, and then you fly to Antarctica using a ski-equipped airplane. And that's a picture of our plane arriving on its skis on the snow, and that's me. And it's about minus 40 degrees, and it's dark because it's August, so the sun hasn't come up yet. It's Antarctica, so August in Antarctica is like February in Boston. I don't have to tell you that our days are getting shorter. They're going to get real short real soon. So this is like February when the days are starting to get longer. And as the days get longer and the sun comes up, that photochemistry involved in Cl2 that I mentioned is going to turn on. So you need really two things to get an ozone to happen. You need for temperatures to be cold, as they are in Antarctica, but you also need sunlight. And that's why it happens every spring in the Antarctic, particularly in September and October. So as soon as we got there, we started doing things like launching ozone measuring balloons. These were actually measurements made by scientists from the University of Wyoming at Laramie, who were part of the team that I was the leader of. We measured things like this. So if you have a look at how much ozone is present as a function of altitude by flying the balloon with an instrument through the ozone layer, if you take a look in August, you're going to get a layer that looks pretty normal. And by the time you come back in the middle of September, you're starting to see this thing get chipped away. And that's what it looks like by, say, the end of September. And that's what it looks like by October. So as you can see, it basically wipes out the whole layer. So the column of ozone that's left is only what's above and below the region where the destruction has been sown. So that's about 12 to 22 kilometers. So let's take a look at where those clouds are. And one way that you can do that is with a laser radar or LiDAR. And you basically shine this incredibly powerful laser up into the sky, and you know what the speed of light is, and you measure how long it takes for you to get a signal back at your detector, so you know how high the part of the light got before it got reflected back down by bouncing off the cloud. And when you do that, you can look at things like the backscatter ratio, and you can find out that the clouds are between about 12 and 5 kilometers, which is exactly where the ozone depletion is occurring. So that's a really wonderful fingerprint. It's the kind of thing that you can talk about. You can explain this to any interested citizen, and they'll say, "Oh yeah, you know, that makes sense." And it's a wonderful illustration of what the problem actually is. I now want to talk a little bit more about some of the things that I personally did. I was the head of the National Ozone Expedition, but I also made some measurements with my own group from NOAA. So we had 4 different research groups, and my group was one of the 4. What we did was spectroscopy, and using it, we were able to measure chlorine dioxide, which is a close cousin of chlorine monoxide. And we did that in those kind of temperatures and those kind of wind speeds by actually collecting light from the moon. And so I have to tell you that as you climb the ladder to the roof, so you can position your mirror in the middle of the night in Antarctica And those were the type of conditions you knew you were really a scientist. It was really fun. So spectroscopy, you guys all know what it is. You've done it in chemistry class. You take the light from the moon and you put it through some kind of dispersion mechanism. You take a look at the wavelength dependence of what you get out. You can put an absorbing substance in the way of between a light source and a detector. And you do that in a chemistry lab, and if you know the length of the path through the absorbing substance, you can say something about how strong the absorber's action is on that light, and you can do that as a functional wavelength. So you're basically going to try to fingerprint the molecule that you're talking about by separating things out by wavelength and taking a look and trying to find distinctive molecular signatures. And this is actually the molecular signature of chlorine dioxide that we were looking for. It absorbs in the blue, collecting blue light from the moon. And we're using a very good sensitive spectrometer to try to see whether or not we can see this kind of a feature. So that was our question. And the way we're going to do it, partly, is by exploiting the path length, and what I think is just a really, really nifty example of how you use these kind of principles in the atmosphere. So what we did was to measure the light from the moon when it was rising or setting. And that's pretty cool because the path length changes dramatically as it rises or sets. So if the moon is directly overhead, its path through the atmosphere is one atmosphere, if you want to put it that way. If the moon is at a 60-degree zenith angle, so 60 degrees off the vertical, the path length is twice what it is if it's straight overhead. That's 3 times at 70. It actually becomes 5 and 7 and 8 times when you get out to these very, very low angles, when it's very, very low on the horizon. So what that means is that if we were to, and that's just a picture of actually close to where we made our measurements, if we measure then the amount of slant column that we see as a function of lunar angle, we ought to do something like this, and sure enough, that's exactly what it is. So the absorption is getting stronger and stronger as the moon sets. I believe that was the moon set in that case. And when we try to do the same kind of thing, say in Colorado, we don't see any, it's undetectable. So that's the kind of spectral signature that we can see. Here's the laboratory signal and the moon signal. Same kind of thing for another band of that molecule, and actually another really beautiful spectrum that we made a little bit later. But those are the sorts of wonderful fingerprints that you can now talk about, again, to people who are just interested. You don't have to be really, you don't have to have a PhD in chemistry to understand this. But really, many people became very interested in understanding how we do what we do. There were many other measurements that were made. I don't have time to talk about them. I just want to acknowledge that people from Stony Brook made some fantastic measurements of chlorine monoxide by ground-based spectroscopy. People from Harvard used airborne resonance fluorescence to measure chlorine monoxide also. Basically, once you put all that information together, you had a host of chemicals, and basically all of them told the same story. There were massive perturbations to the Antarctic chlorine chemistry due to the polar stratospheric clouds. And it was enough to explain the ozone layer depletion and that speaking. So it was an amazing experience, the likes of which I hope many of you can enjoy. And you enjoy them really every day in the laboratory. It's just that having this kind of laboratory like what we're lucky enough to have in neurosciences is very, very special. So I want to say just a little bit about the vortex as a way of introducing some data that I'm going to show you, which is just spectacular. I don't have to spend too much time explaining what the polar vortex is, because after last winter, everyone in America knows. And we're hoping it doesn't come back this winter. So basically, the polar air is very much colder than the surrounding air, and there's a strong wind that functions very much like the vortex in your bathtub, and inside of that region is where you find the coldest and most ozone-depleted air, much like the vortex. So what I'm going to do now is to show you some satellite measurements. These are real data, it's not a model. And And before I turn on the movie, I just want to point out a couple of features here too. So we're going to start in May, which is the end of the spring, beginning of the winter. So nobody knows how depletion yet. It's not cold enough yet. It happens in the May is the end of fall, beginning of the winter, and it won't happen. You have to think about southern hemisphere. It's backwards. So it won't happen until September when the sun comes back. But what you will see is a little bit of action a little bit before that, which is very interesting. So the temperature scale is over here. The ozone's in the middle. Chlorine monoxide's over here. You can forget about nitric acid and HCl. They aren't interesting if you're an expert, but they're not. I don't want to dwell on tonight. The white rings are showing you the edge of the polar vortex. The interior white ring is where the air is really, really the coldest and the most isolated. The black ring is where the solar terminator is. So the black ring is a point beyond which the atmosphere is continuously dark. The black circle in the very middle, the donut, just means the satellite can't see all the way to the pole. So there's missing data where the black circle is. Don't pay too much attention to that. So what you're going to get to see now is what happens as we go into the winter. It's going to get cold, and eventually it's going to get sunlit. The polar vortex is winging its way around, just like it did last winter in North America. As we get into later in May, the vortex is getting colder. Every now and then, suddenly, occasionally there's a data dropout. Every now and then, the vortex gets squeezed, and so then cold polar air goes down to lower latitudes, which allows it to sneak out to the sunlight, which allows some chlorine monoxide to show up. Okay? So that is air that has been now cold enough. We're in June, it's the middle of the Antarctic winter. It's cold enough so if they can just sneak out to the sun, you can get to chlorine monoxide. Isn't that spectacular? And I just love this. And if you have a look at what's going to happen to ozone, what you'll see in just a couple of seconds is that as we get later and later, the vortex is now getting bigger because the stratosphere is getting colder and colder. Chlorine monoxide is spreading over a bigger region. It's going to start to eat out a remarkable hole in ozone that's going to look not like the things that you are used to seeing, not like those wonderful images of the ozone column, because you'll get to that eventually. But first what you're going to see is that in the region of high chlorine monoxide, you're going to just start to see that. That's photochemistry at work. You get actually a donut, if you will, before you get a hole. Because there's still ozone in the middle because it's dark. So the region that gets depleted first is that edge of the vortex where there's enough CLO, it's cold enough, but you also have enough sunlight. How cool is that? I mean, you know, it's just amazing. So by the end of August, you're starting to see a significant amount of ozone loss, and pretty soon, basically, you'll fill in the whole vortex. By the way, the black circle is getting smaller now because the sun's coming up, so everybody's getting sunlit. The ozone loss is getting very severe, and basically it's completely destroyed, as I showed you in the blue sun. Now what's going to happen as we go from September into October, the vortex is going to break up. I think we have enough time here that we're going to actually start to see the hole fill in. And that's filling in is just from mixing of high ozone air from outside into the vortex. So there's a lot of ozone outside the vortex, and as we get later and later in the season, it will ultimately start filling it in. It might stop before that happens. I'm not sure. And you can already see it's getting smaller, so it's getting degraded by mixing, and eventually it'll just fill up. So let's talk about what the nations of the world decided to do in the face of all of this evidence. They decided to do something remarkable. They passed the UN Treaty called the Montreal Protocol, and they decided to phase out chlorofluorocarbon usage everywhere. They started out by phasing it out in the developed countries. They gave the developing countries an 11-year grace period, and as they needed to use more and more chlorofluorocarbon, substitutes were available, and so the developing countries also came along. So what you see is that the amount of chlorine in the atmosphere was increasing, and the ozone hole happened. If we never had a protocol, this would have happened, and it would have been a planetary catastrophe. The ozone layer would have collapsed. Almost, we'd be in bad shape already, actually. What happened instead is that we're following very much the agreement that was amended in Beijing in 1999. So I should just mention the original Montreal Protocol signed in 87 was amended time and again as the diplomats met, just as the Kyoto Protocol was amended. There was the hope of amending it in Copenhagen, which didn't materialize, but that was the hope. In the case of the Montreal Protocol, the amendments, as you can see, were quite significant. So they went from the original protocol to less emission, still less emission, to essentially zero emission, which is where we are now. So the CFCs are slowly decaying over, say, the next half century, because just as Moline and Rowan said in 1974, they have a lifetime of 50 to 100 years, so it takes a long time to have them go away, even after you stop emitting. And that's why this is so slow. But it will eventually get there, and by about 2060, we can expect that the ozone hole will actually close. It may close sporadically between now and then. I think it will actually. We'll start to see improvement, but it won't close continuously until 2060. We'll have some years with it, some years without it, something like 2050. So now we're going to have a quiz, and it does not count for a grade. So be daring and tell me who you think country X was. These are quotations about the negotiations that were done from someone who was very involved in them. And he talked about country X as being skeptical about the theory, said, oh, even if it's true, it won't be harmful. That was the official position of country X. Country Y was fairly similar, but they were actually even tighter with companies, and so they were kind of friend of X. Country Z and its government and its allies were the ones who went into every meeting saying, we must have a protocol, we must phase out these molecules, they're bad for the environment. So would anybody like to give a guess as to who was X? Skeptical of that, it's only a theory, it's not going to be bad. Come on, great. Yeah. Russia. You think X was Russia? Okay. Anybody else? Yes? USA? How many people think it's USA? How many people in your heart do think it's USA? Okay. Who do you think was Z? These are, really environmentally conscious. Let's do something about this.
Germany.
Norway.
Norway?
Yes.
USA.
Some people know. Now let me just say this. I know I just said a lot of things about chemistry you guys are not going to remember. I think you're going to remember this. Because it's telling you something really important. It is true that the United States and its allies, which included Sweden, Norway, Canada, and Japan, so people got some of those, were the ones who led the resolution to get to a legally binding protocol. The most skeptical country was actually the UK. And the European Commission, which was basically representing France and Germany, two countries that we think has been pretty environmental today, had a position pretty similar to the UK. So I'm showing you this in part because it ought to give you hope. It gives you hope that, in fact, the entrenched positions of different countries weren't always that way. There is nothing fundamentally, it is not impossible for the United States to be an environmental leader. We've done it before on this issue, and actually also on many other issues. I talk a lot about that in my course, so I encourage you to take it. But let's talk just a little bit more about what happened in the United States that was so different from Europe at that time. And I'm showing you this so that you can contemplate the sales of chlorofluorocarbons as a function of year. Here's the American sales. Boom, all of a sudden, took a nosedive. The rest of the world flattened off a little bit but kept going, and so the total did something like this. The rest of the world was basically zero. At that time, they were selling to everybody else, and so that's pretty much Europe. So why did this happen? It's not because the ozone hole was discovered, because the Montreal Protocol was signed. It's not even because the ozone hole was discovered. What happened in 1974? Anybody remember? I showed it to you already.
The paper published?
Moline and Rowan published their paper. So people became aware of this problem. Environmental groups, particularly the NRDC, made people aware that, that things that they could do that were practical could actually bring tremendous pressure to bear on solving this problem. And what did you have to do? Well, you had to take those spray cans that were in your medicine cabinet and do that. How hard is that? I remember actually TV commercials, get on a stick to save the ozone layer. This is what they were talking about. And so millions of Americans did it, and the sales of chlorofluorocarbons in the United States started dropping even before there was any kind of ban on their use. It wasn't very difficult for people to use, and it basically made what had been really good business, a growing business, into bad business in the US, where it was still going on in the rest of the world. So Europe didn't do the same as we did. It put tremendous pressure on those companies because they now had overcapacity. They had the ability, they had lots of plants, they had the ability to produce way more than they were going to be able to sell. And any good company, when it finds out that it's into a business that isn't working, wants to get out of the business. So it isn't true, as you may have heard rumors that somehow the American companies were ahead of the Europeans in finding substitutes. I know actually that is not true. What is true is that they had way more pressure to get out of the business, and they were willing to compete to make something else. And so they made the substitutes. But fundamentally, the driving force for it was people. Let's talk about just a little bit about the other applications. I don't want to spend too much time on this because I do want to get on to talk about climate change a little bit. But basically, there were successes in sector after sector of application of chlorofluorocarbons. Solvents were replaced in some cases with lemon juice. Foam blowing agents were found for styrofoam, and that actually put a lot of pressure on, people put a lot of pressure on McDonald's because the Big Mac used to be sold in a styrofoam container. People actually demonstrated against the styrofoam containers at McDonald's for a while. So let's just talk about the rule avoided very briefly. I kind of already alluded to this, but that's what was happening in the measurements from the 50s up to about almost now. I'm missing a couple of years, but they're not significantly different. And this is what would have happened, and this is what's going to happen. So it's been a tremendous achievement. We're beginning to see recovery in the global ozone layer. We can average over the whole world and get a signal now. We can't quite do that in Antarctica yet because it's just, it's a smaller part of the world, so everything doesn't value as much. But if you go ahead and average the whole globe from satellite data, you can start to see recovery very slow, but we're starting to see it in good latitudes. So what happened with ozone? Well, again, it's another interdisciplinary success story. Science showed fingerprints that made this problem perceptible to people. It was clearly personal. Cancer is very, very personal indeed, and so are cataracts, as well as, of course, the impacts on nature. Rabbits with sunglasses don't, do too well. Consumers and environmental groups were able to focus attention on doing something practical that kickstarted a major change, and certainly engineering and innovation to actually replace the chlorofluorocarbons in the various applications was huge. It was also accompanied by very skillful diplomacy. So it was a fairly cheap problem to fix, no question. It wasn't on the scale of climate change. It was only a few billion-dollar industry. But it's very interesting to notice how people working together actually were able to deal with this problem. Personally, as a scientist, the fact that I was able to be involved in the fingerprinting, and I also had the chance to interact with engineers who were developing those substitutes was fantastic. And we did that as a result of the assessment process under the Montreal Protocol. So I would go to those meetings and meet those people, learn about what they can do in a refrigerator or really challenging problems, fire extinguishers, all of those applications, one by one, substitutes were found for the ozone-depleting compounds. So the question that I think is really important is this one. How many of the environmental problems of today could MIT help solve if we work together more across disciplines? And that's one of the things that I am devoted to doing as founding director of the Environmental Solutions Initiative at MIT. I'm going to talk about that in just a second. I want to talk just a little bit more about climate change because it's a good illustration of some of the tying together some of the things that I've already talked about, how they also raise many of the same issues. So if you look at carbon dioxide, as we all know, it's gone through an unprecedented increase. This is 10,000 years of Earth's history in ice cores. Remind me of lead in ice cores? And fairly stable for about 9,900 years, and then this tremendous increase that's happening in the industrial era. That is changing the planetary energy balance, and it's also acidifying our oceans. The concentrations are actually higher than they've been in more than 800,000 years, probably more than 1 million years. But certainly in the last 150 years or so, it's undergone a tremendous increase. So, when there were those guys on the planet, nothing was happening. When there were those guys doing pyramids, not much. Romans built the Colosseum, not much. It wasn't until the industrial era, and all the benefits that it gives you, all the wonderful things like electricity and heat and toilets and everything else that are so tremendous about our ability to industrialize. It adds to our health, and it also is deleterious to our health through its effect on the